1D signal. This is depending on time. Okay? And this is the time axis. I can sample these signals, and sampling means that I collect the amplitude of the signal periodically. Okay? The spacing, let me call the spacing D. Okay? D represents the spacing between samples. So, we know that in this case, the frequency, the sampling frequency, okay, the sampling frequency is equal to 1 over D. Okay, it is the inverse of the sampling interval. And we also know that if the sampling frequency is at least larger or equal than the bandwidth of the signal. Okay, what is the bandwidth? So, if we make the Fourier transform of this ST, okay, so if we make the Fourier transform of this one, then we get a certain bandwidth occupancy. So I put the frequency here. I don't know, this is the bandwidth occupancy. And this is F max, the maximum frequency of bandwidth occupancy, which is the maximum frequency. So the sampling frequency should be larger or equal than 2 times the maximum frequency. Fine, okay? Now, if the signal is a sinusoid, that means that being a sinusoid, this spectrum is represented by 2 lines. Okay? So if this one is a sinusoid with a certain frequency f0, and then I have f0 here and minus f0 here. Now the maximum bandwidth, how much is that? Is f0, right? Okay, so the sampling frequency is larger or equal than 2 times f0. Okay? Which means that the interval, okay, should be, which is the inverse, should be lower or equal than 1 over 2 times f0. Okay? Which is 1 over half times 1 over f0. Okay? Which is equal to 1 over half times the period. Okay? This is the period, we call it t period. Okay? So that means that the sampling interval should be smaller or equal than half of the sampling or half of the period of the sinusoid. Or equivalently, I should have at least 2 samples per cycle. Okay? So I need to have at least as minimum. Okay? So I can rewrite as 2d, okay, smaller or equal than tp, which is the period of a signal. Okay? Remember that. Now let's start with the array signal processing. Okay? So everything I said, should be, for the telecom it's more than known, okay? And for the other is quite well established. So now let's start. What is array processing? In array processing, what's happening is the following: that I have a wave field, and the wave field is propagating the space. And so you can imagine you have the acoustic wave field. The acoustic wave field means that when I speak, I have the acoustic wave, the pressure wave, which propagates in space. Okay, and so it spreads uniformly in space or non-uniformly in space, depending on the medium or the excitation. For instance, if I speak this way, then my goal is to spread the wave field in a certain direction and attenuate in some way the wave field in the direction where, I mean, on the other direction with respect to where I put my hand. Okay? This is called the directivity. So directivity is the property that the wave field has a different amplitude whenever it propagates. Now, so what's happened with that? You know, once we have this hypothetical wave field that is propagating, so you can imagine that, you know, I make it, you know, graphical. Okay, so you can imagine that you drop a stone, okay, into the water. Then what's happening is that you generate these waves, and these waves propagate. So the propagation depends on the propagation velocity of the medium. So it depends on the medium. So I don't know if it is water, if it is air. You know, if I propagate the pressure wave into the water is different than propagating the pressure wave into the air. Okay? But then, you know, what's happening is that, I mean, if I look at that in space, so, you know, I can see something that I try to picture, okay? So this is the, you know, I am plotting a waveform, okay, along, you know, this is the waveform, along a wavefront, okay, and overall this one represents a wave field. Okay. The waveform is the signature in time that propagates. When you throw a stone into the water, if you freeze the field and you look at the specific, you know, signature in time, that is the waveform, which is propagating. This waveform is propagating, okay? Where? It is propagating along a surface, and this surface is the wave field, the wavefront. The overall, so if I take a snapshot, when I throw a stone into the water, then I see this perturbation. Okay, this is the wave field. So the wave field propagates in space along the wavefronts that carry the corresponding wave field. Okay? Now, so if I don't do anything, okay, there is no array. So the array does the following. This is propagating in space, okay? It's three-dimensional space. So now put along wherever you like, okay? So put along this strange line, a set of devices, and these devices are measuring the wave field, okay? So these devices are measuring the wave field in different positions. So the positions where I measure the wave field, okay, these positions are known. So here I have a set of sensors. These sensors are measuring the wave field. So that means that these sensors are distributed in space. So what I should have, these sensors are, I have a set of sensors, many sensors, okay? And they are in known positions. Now these sensors, what they do, they measure, okay, the wave field in a particular space. They measure. Similarly, I sample. When I sample the signal, I measure the signal in a specific position in time. Now these sensors measure, sample the wave field. Okay, so sensor in known position sample the wave field. So array processing is processing the signal coming from a set of sensors distributed wherever in space, okay, and extract from the processing some information about, for instance, the characteristic of the sources, how many sources I have, what is the, the original signal from the source, and so on. Because for instance, I might have a second source, which is positioned in another place, which is generating, its own wave field, and the corresponding waveform can be different. Okay, so this one is propagating this strange, wave field. So, there is this strange, I don't know, it can be a piece of signals or whatever. Okay, so you see the waveforms are different. So each one has some specific characteristic of, the waveform that is transported, over the space. Now, this is the setting of array processing, and now I specialize in some specific configuration. But what is important is that the sensors are sampling the wave field. Now let's go. These are the different arrangement of the sensors. So these sensors can be arranged as a linear, or can be arranged as a rectangular and regular in space, or can be regular in plane, or can be circular, or these are planar, or can be linear but not regular. So this is linear but not regular. So in order to say that this is linear, but this one is linear, the second one is linear, but is uniformly spaced. So this arrangement of a sensor is called a uniform linear array. Let's see, uniform linear array. Now this configuration, so this configuration, the configuration for uniform linear array, that in jargon is called ULA. Uniform linear array is the configuration of sensors that we analyze. But nevertheless, there are many other configurations. There are configuration of rectangular, and by the way, there are configuration of antennas that are, for instance, deployed, in a cubic. So you can have a cube of sensors that are sampling the wave field in different positions in space. So you might have an arrangement of three-dimensional sensors, which means you have an arrangement of sensors, or this is usually called array geometry, which is the geometry of the arrangement of these sensors, which might be in a cubic, which might be in planar, and for instance, there is one project now running, which is carried out by some friend of some of you, which includes the sensors that are arranged in cylinder. Just to say. So there are different. Each arrangement is dedicated specifically to isolate the signal of interest, because in some cases my goal is that I arrange the sensor in such a way that the sensor is arranged to extract as much information as possible from the experiment itself. Now, so let's consider, this is the array geometry that we will consider here. So, but don't be surprised if in life you will find a totally different arrangement of sensors. Now, for instance, if you talk with electromagnetic people, they talk about conformal arrays. Conformal arrays are an arrangement of sensors that are conform according to some property of the array itself. And in some airplanes, in some airplanes, there are array of sensors that are conformal on the cockpit of the airplane. So it depends on case by case. Okay, these are to check for weather. But you know, anyway. So going to the point, okay. Going to the point, I mean, we consider the uniform linear array, and this is the arrangement. Right? So you know, what we have is that we have one source. Okay, so we have one point which is emitting a signal, and the signal emitted by the source is ST. Okay, so the source is emitting a certain signal, which means, I don't know, if you have a signal here, this source is transmitting, is generating a certain path, which I indicate just as a path. You know, the source might emit, you know, more esoteric and complicated. Like, you know, if I speak to them, whenever I speak, the way that propagates is not a path, is pop, and you know, you see the behavior of the speech, and you know what is the waveform of the speech. Okay, so this is what propagates. Okay, over here. Now you know this is propagating in space. So after a certain distance, which is what I indicated here, after a certain distance, you know, the wavefront is curved. Okay, because it's due to the spreading property of the wavefield. So you know it's curved. You know, and we have a set of array, which is a uniform linear array. So we have a uniform linear array, and we have a curved waveform. Now, if the array size, this is an aperture. This is called aperture. Aperture is the entire distance. Okay. Now, if the array aperture is much smaller than the relative distance, okay, so the distance much smaller than the aperture. Okay, so if I'm in this setting, then what I can say is that the wavefront is approximately planar. Okay?
The distance would be smaller than aperture.
Okay?
The distance would be smaller than aperture.
No, the distance should be bigger than the aperture. I wrote the inequality. Distance, I have space. Okay, if the distance is very big, okay, now you know it's we can quantify, but you know, the distance should be very big with respect to the aperture. Now, to make an example, okay, to make an example of. To make an example of acoustic, for instance, okay? If I speak here, and you have your own array, and you have an array of sensors, and you put these sensors, you know, at this spacing, like a Wii, okay? Consider the Wii. Now, in that case, if you put the array at this distance, compared to my voice, so you have the array of the Wii, which is that big, and my distance is from here to there. Now the wavefront is curved. If the distance, you know, is in the order of 5 meters from here to there, then you know the far field approximation of the array holds true, which means, you know, is reasonably well approximated as a planar. Okay? There are contexts where the planar approximation is never met. Never. And these field, this application area, which we are not discussing here, but perhaps some of you is, you are probably making shopping for different courses to do next. Okay. So this area is the oil exploration area. In oil exploration, you never have a planar wave. The wavefront is always curved. Now, just to use this, I write here. Just to give you, just a flavor for that. I'm making this extension, these comments, just because some of you is in a position to choose what to do next, okay? So assume that you have a source here, and assume that you have your array here, which is perfectly centered here, okay? And this is the position of your array. You call this axis as x, just to give a number, okay? And this distance is h. So if I want to find what is the propagation delay to go from the source to this position, which is x naught, okay? So then the distance is the Pythagoras, so which is h squared plus x squared, okay? So this is the delay. Now, what is the far field for the array? The far field for the array means that if this is the center of the aperture of an hypothetical array, then I have some delay from the beginning of the array and some delay at the end of the array. So if this is x naught is the center of the array, you have x naught plus delta x divided by 2, and then you have x naught minus delta x divided by 2. Okay? Now, what you need to calculate is that the distance, the relative distance with respect to these 2 points. Then let me change the color. Okay. Now the distance from there to there. Okay. The distance is h squared plus x plus delta x divided by 2, everything to the square, then square root of. And the distance from the other is square root of h squared plus x minus delta x divided by 2 squared. Okay. Now, what does it mean the far field approximation? Now, the far field approximation means that if I take this h and I collect this h, so I have h squared, then I have square root. So for this and that, okay, in 2 cases, let me cancel. So I make one computation call. Okay, so this one is h, then it is square root of 1 plus x plus minus delta x divided by 2 to the square. Okay. And everything divided by h. Now, you see that you have x plus or minus something. Then this one is not linear this way. So what I need to write, that if I compute the delay with respect to the center, okay, so the delay with respect to the center is with respect to h squared plus x squared. So I have the delay with respect to the center, which is h squared plus x squared, square root, which becomes h 1 plus x divided by h, everything to the square. Okay, so this incremental distance should not change the delay much to guarantee that the Taylor series of this square root can be well approximated by the first order. That's the point. And this is guaranteed that when this h squared and this delta x, you know, this term is much smaller than 1, because I can calculate the Taylor series on that. So if I can, you know, if I can make this way, then I am in the far field. But in many oil exploration application, you are in this setting. This is the oil exploration satellite application. In oil exploration satellite application, you have a source here, and you have the array there. Now, if you, for instance, if you have a bistatic radar, or if you have a oil exploration, in oil exploration, what you do, you need to search for these layer structure staying on the top. So you are staying on the top, and you want to see under the surface of the earth, under the surface of the earth. So what you do, you generate a source, which is an acoustic source. You make a vibration on the top. Then these vibration, let me change the color. This vibration propagates, is reflected back, okay? So it is reflected back to the array in different points. But usually these arrays in the order of 2 to 4 kilometers. Okay, this is the array arrangement of sensors. This thickness is in the order from 500 meters up to a couple of kilometers. Okay, so you have 2 kilometers by 2 kilometers. Now you can mimic the experiment as if you have a virtual source, which is here, which is generating the ray. Okay, similarly as if, you know, I have a source position in the surface. Now this source is called the mirror source, and then the distance, okay, is 2 times 500, so it is 2 times 500 or 2 times 2 kilometers, okay, which makes a 1 kilometer and 4 kilometers. Now, putting at the end, you know, the distance of the source is the same or approximately the same as the size of the array. We are not in a far field. We are not in a far field for the array. We are in a near field, and my wavefront is curved. Okay? So you have some application. You know, the curved wavefront is offering some nice features, but then, you know, some impairment. So it depends on the case. Acoustic now is using the curved waveform. It's using curved waveform because the sensors, the microphones, are arranged in like you have an orchestra, okay? You have the orchestra area, and you put the sensors around the stage, okay, in front of the stage. Then you know you have an array of sensors, but the singer, they are very close to the array. So you don't have, again, in this case, you're not in far field. Okay? So we are not discussing about near field. Okay? So we are not, you know, we are not discussing in the near field. So we are in far field. Our wavefront is linear. Okay? But keep in mind that curved wavefront exists. If you look at the homework of the last year, it is for curved wavefront, and it is solved by, you know, by estimating the time of delay. So the method for curved wavefront is different from the method that we discussed. So there is a big difference, you know. Curved or linear, you know, you have different strategies. Okay, so we only touch the linear the uniform linear array and far field or linear waveform. So going to the point, let's make some analytics on that. Now, so assume that I have a source, okay, and I have a curved waveform that locally within the aperture of the array can be approximated as linear. Okay? So we are in a far field approximation for the array processing, which is different from the far field approximation in electromagnetics. Okay, just to clarify, the far field approximation for array processing implies that the source is very, very far away. For electromagnetic, it depends on the wavelength. Okay, just to clarify some aspect. Now, assuming that I have a narrow band source. What is a narrow band far field source? Far field is a far field for the array, and this is the source. So the source is ST AJ omega 0t. Now, this source is representing an amplitude modulated signal. Okay, so that means that if I look at the wavefront, and I have a possibility to take a snapshot along the wavefront to look at the waveform that is propagating. The waveform, I keep on playing with these words. So after a while, you get practice. Okay? So the waveform has a shape with ST as an amplitude, okay, and omega 0 as the carrier. Now, I need the board for that. I started too early for this. Okay, let me make this here. So, looking at the narrow band, I'm making these refresh for non-telecom, because the telecom, they know this, what I'm saying, as more than their nose, okay? They more than their nose, okay? So when I say ST AJ omega 0t, okay, which I can write as ST cosine omega 0 t plus J sine omega 0 t. And by the way, ST can be complex, so can be S real t plus J S imaginary t. Okay, so this term is called the modulating term. And that one is called the carrier, omega 0. Now, typically, the frequency of the spectrum content of ST is much, much smaller than omega 0. In other words, it means that if I take the Fourier transform of ST, okay, the Fourier transform as a support, so is limited to a certain maximum frequency. Let me call this B max. Okay. This is the frequency. Now, so B max is much, much smaller than F0, which is F0 is omega 0 divided by 2 pi. Okay. Now this condition is called the narrow band hypothesis, or narrow band condition. The narrow band condition implies that if I look at these signal in time, this signal has a very slowly varying component, which is ST, okay, and it has a very fast varying component, which is given by the cosine or the sine. Okay. So that means that this interval, which is the period, okay. So the period is the inverse of F0, right? And then this is 2 pi divided by omega 0. Okay, this is the period. And the period of the other, approximately, which is the decorrelation interval, okay, is approximately 1 time over the max. The max. Okay. So what we noticed that with respect to the sinusoid, okay, which is the carrier, with respect to the sinusoid, the signal ST, which is the envelope, is changing very, very slowly. Very slowly. Now, if Bmax is much, much bigger, much, much smaller than F0, it means that, you know, if I make the ratio between Bmax and F0, I calculate F0 divided by Bmax, okay, is approximately the number of cycles of a sinusoid before ST decorrelate. Okay, so this number is very, very big. The order of 100, 500. Okay, so that means that, you know, the envelope is really, really slowly moving. Questo è qua, no?
Non siamo del corso, però stavamo andando giusto.
Voi non fate casino,
No, no, non stavamo.
neanche andate dentro fuori.
Vabbè, no, comunque stavamo andando.
So, you know, this is the behavior. So, you know, it's, I mean, within that interval, it's slowly varying. Now, this trick about fast varying and slowly varying is relevant. Now, let's go back to the point. So, you know, if the experiment is done this way, so that means that at the decayed sensor, so, you know, I have this sensor, let me zoom it, and these sensors are measured. So 1, 2, blah, 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 and then on the end, okay? So I have a decayed sensor, and then an end, okay? So, you know, what I measure now is the delay, the propagation delay between the source and the decayed sensor, okay? So, you know, what I measure at the decayed sensor? I measure at the YKT, which is the signal measured at the decayed sensor depending on time. What is that? Is the waveform, okay, delayed by tau k, okay? So tau k, you know, is the delay from the source to the k receiver, plus wk, which is the noise at the k sensor. Now, so tau k is the delay from the source to the k sensor. Okay? Now, you know, usually I don't know the distance. Okay? So tau k is a parameter of the problem. Now, let's assume, that's another assumption, okay? Let's assume, which is also implied by the narrow band approximation. So let's assume that, you know, the delay of the envelope, or the shape of the envelope, between the first sensor and the last sensor, they are approximately the same. So if if my source is coming from this way, okay, and this is my array, so what's happening is that my waveform is hitting this sensor first, and then that one has a loss, okay? So there is a delay. So, you know, if I represent this delay, it comes out something, let me sketch. So imagine, you know, I have my, let me put it this way. So these are my sensors, okay? And my source is in this way, which is, I have a wavefront which is impinging this here. So it's coming from there, okay? And so it's touching the sensor 1, okay? This is n minus 1, this is n. And then after it touches the last one, okay? So, you know, what's happened? It happens that in time, if I look at the ensemble of these signals in time, so what I can see that, you know, each of these signals is characterized by an envelope. And then is characterized by the sinusoid, which is bouncing between the envelopes. okay? So, you know, the sensor number 1 is heated as a first. Then, you know, you heat the sensor number 2, number 3, number 4, but you know, then you heat the sensor number n minus 1. But you know, since the envelope is so slowly changing, even if the envelope theoretically, okay, there is a delay in the envelope, okay, this is the delay of envelope, okay, between 1 to n minus 1. The delay of the envelope does not change the envelope itself. So the envelopes are all the same, approximately, of course, okay? So that means that, you know, for the n minus 1, I have a difference, so the sinusoid inside has changed the phase, but the envelope is approximately the same. So what we see, you know, what we conclude that we can set up an experiment such that the st minus tau 1 and then have aj omega 0 t minus tau 1, okay, which is the signal at the sensor 1. Now at the sensor, let me write here so it remains the. I'm inventing this plot, guys, so you know. Okay. And then I have the you know, the signal st minus tau n minus 1. And then I have aj0 t minus tau n minus 1, okay? So these two signals are the signals that are received by the two sensors. Okay? So what I conclude here, I conclude that st minus tau 1 is approximately the same as st minus tau n minus 1. So the envelope, okay, is not changing versus the array. Okay? The envelope doesn't change. What changes is, you know, the sinusoid, because the sinusoid is affected by tau 1 and tau n, and so according to the delay, the phase has been changing much. Okay? So, you know, and that, aj omega 0 t minus tau 1 is well different, okay? It's different from aj omega 0 t minus tau n minus 1, okay? So now let's go back and use this property. So the envelope doesn't change, but you know, the sinusoid and the phase of the sinusoid changes. Now, you know, the envelope is related to the information which is transported by the wavefield, the voice, okay? So, you know, I have the voice, let me say, this is the voice at the sensor 1 and it's the voice at the sensor n minus 1 or the voice at the sensor n. Now, what I'm saying is that the voice is the same to every sensor, but you know, the carrier is different. Okay, the carrier is the sinusoid which is represented here. So since the voice is the same or approximately the same, so the envelope is approximately the same. So what we can conclude, we can conclude that you know, neglecting the propagation delay from the source to the array, okay, this is you know, this delay is irrelevant in general. Then we can model the overall system such that the envelope is equal to the envelope when I transmit it, when I generate the signal, plus a phase that depends on the array position. Now, putting in a general flow. So, reviewing this concept. So, the delay due to the propagation from a source, it depends on the propagation velocity, okay, and at the frequency omega 0. So st minus the maximum delay is approximately equal to ST minus the minimum delay. So here I'm not saying that the waveform is coming from whatever direction. Okay, so the array size is compact, is small again. We can say that the yk of ST minus tau k is not depending on tau k. And the only term that depends on tau k is the second one, plus and minus. So, you know, the only term that depends now on the array is this one. Now, look at that. If I isolate that, you know, the transmitted source, ST, and then I have this term, which is AJ omega 0 tau k. But you know, this one is a phase. So I have a phase that depends as a function of tau k. And tau k depends on the array geometry. So how the sensors are arranged. Now, so let's analyze this part. So looking specifically to that, you know, looking at the signal that I receive. So, you know, I receive a signal that depends on tau. So what we need to do, we need to calculate the tau at the different sensor in the array, assuming that I am generating a narrow band signal. So I'm only looking at the impact of the sinusoid because the envelope is not relevant for us. I only look at, because the envelope remains the same. So if I take a photo, the envelope across the array is the same. So if I have a possibility, you know, to take a photo of when I throw a stone, imagine that when I throw the stone into the water, okay, I generate this wavelet, okay, and it is propagating. When this wavelet is propagating, I put an array that compared to the curvature of the wavelet is very small. So if my wavelet is propagating here, is propagating, then I put an array that big. Okay, what I see is plane. And then, you know, the array size is smaller than the propagation of these, you know, this wavelet. So the envelope is the same. The only that changes is the sinusoid that is transporting the signal. So now we look at the sinusoid. We look at the sinusoidal part because the envelope it doesn't change. Now looking at the sinusoid, so we have a sinusoid in you know, in space, okay? Because I mean, now you need to forget for 1 minute that I throw the stone into the water, but I rather look at the perturbation very far away from the source. So the wavefront is linear, and you know, and since the wave field is transporting a sinusoidal waveform, I see the sinusoid in space. So this is what I see in space, okay? So this is, you know, my sinusoid. Now, imagine that with respect to the array, imagine that the source has an angle theta with respect to the array. This theta, this angle theta, is called the direction of arrival. DOA, okay? So, you know, what's happened is that since my wave field that is propagating in the space is represented by a waveform that is sinusoid, so what I see, if I hypothetically see this wave field that propagates, is like you know, a house roof, okay? You know, in Italian it's called ondulina, you know. So it's like the roof of the house, okay, which is oriented with respect to the source, okay. So the source is in this direction. Then you know, I mean, the wavefront are perpendicular to the direction of the source, okay. These are called also isophase by the electromagnetic people, okay. So you know, the wavefront are isophase, but you know, in our case, since we generalize the concept of isophase to the concept of transporting whatever signal, then the wavefront is a locus where the waveform doesn't change. Okay. So, Anyway, so these are the, you know, the wavefront that are planar. What is the mutual distance between two eyes of phase, or between two wavefronts? Now, the mutual distance between two in space is lambda. Lambda is the wavelength corresponding to the sinusoid at the frequency omega 0. Now, the wavelength depends from the physics. The wavelength depends on the frequency, on omega 0, and depends on the propagation velocity in the medium. Okay? So, if, you know, if we're talking about electromagnetics, then the propagation V is equal to 3 times 10 to the power 8 meter per second. If we are talking, this is for electromagnetic or light. Okay? If we are talking about air, acoustic wave, okay, which technically is better to call compression wave, which is compressing into the air, then the number is 335 meter per second. Okay, again. Okay. If we are looking at propagation into the water, I think should be in the order, I don't remember, you can check, but it should be in the order of 500 or 600 meter per second. Okay, this is in water. So, you know, it depends on the case. It depends on the context. Like, for instance, if you have the sonar, then you are looking for this. If you have music and you're using an array processing for music, then you look at this number. And if you have electromagnetic like antennas, then you look at the other number. Okay? So, you know, we know from the physics that lambda, okay, is equal to the propagation divided by the frequency of the wave. This is another quantity that we know from the physics. Okay? So, given that, you know, let's work. Now, assume that I take one sensor as a reference. So I start considering that sensor number 1 is a reference. So what I do, I calculate the relative distance between one sensor, or every sensor, and the sensor number 1. Now I calculate the distance, then I put my sensor at the distance d. D is equal to that. My sensors are doing what? Are measuring the wave field. But the wave field is sinusoidal. So it's measuring the wave field that is sinusoidal. So it is sampling spatially the sinusoid. It's spatially the sinusoid that has a period that is obtained by taking this sinusoid that is propagated in this direction, cutting along in the diagonal direction with respect to the propagation. You see that? Okay? So you are cutting, we are cutting the sinusoid here, the spatial sinusoid, which is propagating in space. So cutting in this way, if lambda is the period in this direction, the period by cutting on the other direction depends on the trigonometric, so it depends on the sign. Okay? So you scale by the sign of the period. And so, if, for instance, if theta, which is the direction of arrival, is equal to 0, then the period along this direction, since all the wavefront is perpendicular, the period is infinite. If, on the other hand, my wavefront is coming from this direction, sine theta from theta equal 90 degrees, which is pi divided by 2, then I have that the array is perfectly sampling the spatial sinusoid along the direction of maximal frequency. Okay? So then we have a concept that, as we know, except that the new part is that we don't sample the signal in time. We sample a signal that is propagating in the environment in space. So the new part is the space sampling by the array, by the uniform linear array. Okay? Now, So let's consider now the delay. So if I look at the delay, then I can easily calculate that the delay at the kth sensor, any arbitrary kth sensor, is equal to the delay at the first minus d divided by v multiplied by sine k minus 1. So the delay at any arbitrary k sensor depends on the position of the sensor and it depends on the theta angle. But theta is the same in directional arrival. So that means that the delay depends on the directional arrival. So now, let's put this new definition of delay, which is just the definition of delay, onto the formula of the signal that we calculated before, which is copied here. And now what I get? I get this. I get that the signal that I receive at the kth sensor is equal to the signal of the envelope multiplied by aj omega 0 d divided by t k minus 1 sine theta. Now this component is a spatial. Then I have aj omega 0 t plus numbers. So now if I freeze the time, which is in jargon is called take a snapshot, like a photo. Okay? So if I take a photo, which is like there, this one is a photo, okay? Because I freeze a certain time. When I freeze a certain time, what I measure, this is the temporal part, but since it is free, it's constant. Then I measure aj omega 0 d divided by v k minus 1 sine theta. So I have a spatial sinusoid, which is uniformly sampled in d, distance is d, and it depends on the frequency, it depends on sine theta. So I reduce my problem to having a spatial sinusoid, which is highlighted there. So, this is, depends on, in conclusion, this is my problem. So my problem reduces to have a spatial sinusoid d divided by lambda, which is sampled, already sampled, okay? And the frequency of this sinusoid, which is a spatial frequency normalized because I've already sampled, it depends on theta. Now, in principle, I could stop here. Because I could say, okay, everything you know about the sinusoid, maps here. And estimate the frequency of the sinusoid is equivalent to estimate the directional arrival. Because look at this. If you see this one this way, so it is aj. So if I write aj omega x time k minus 1, okay, that is a sinusoid. That is a spatial sinusoid. Okay? So we have a spatial sinusoid. So we got a spatial sinusoid. So I can say, if you need to estimate the directional arrival, then you just estimate this omega x, which is a compounded. Okay? But this omega x depends on theta. So it depends on theta through the sine. Okay? So if I put, now I took two space here, but here, you put it. So if I just put everything in perspective, let me copy the frequency. So I have 2 pi, so aj 2 pi, then I have d over lambda, okay, let me put just lambda, then I have sine theta. Now, this term is omega x that depends on theta. Then what I do, I sample. Now sampling means time, rather than putting x, which is the position of the sensor in a continuous way, I put the position of the sensor referred to the first sensor. So it is d time k minus 1. Okay, so this one is the discrete sample position. Okay? So, you know, I can also elaborate a little bit on that. So I can say that, you know, if this one is a frequency, then lambda divided by sine x, sine theta, it is lambda x, which is the period along x. That's what you see there. Okay. See? So, you know, I mean, everything that I can see here is similar to what I see there. Okay? So, you know, I have a spatial sinusoid. Now, what is the major difference? The major difference is that the mapping between the direction of arrival, which is theta. Okay? You know, the maximum theta is 90 degrees, so between 90 degree and 90 degrees. The mapping is represented by a sine. So, and on the vertical axis, at omega x. That depends on theta. So the dependency of the frequency with respect to the direction of arrival is nonlinear because there is a sign in the middle. But you know, once I know how to estimate the frequency of the sinusoid, once I have a Kramer-Rao bound for the frequency estimation, I have the Kramer-Rao bound for the direction of arrival. Because you know, it's simply a mapping. The mapping is represented by the sign. Now, my recommendation, you know, I will insist when we do exercise on that, is that you represent the direction of arrival in degree. Don't use radian, because you know you will see in 1 second why. You know, you are better not to use a radian because we have a radian for normalized angular frequency, and see if you put the radiant on the direction of arrivals, after a while you don't understand what is this particular angle, if it is direction of arrivals or spatial frequency. Now, so you know everything we said is indicated here. So you know, I mean, just to reread what we already discussed. So the signal along the line of sensor is a spatial sinusoid for a fixed t. Okay, this fixed t is called a snapshot. Okay, with a spatial angular frequency, which is, you know, is a spatial sinusoid which is cut along the one direction, and the spatial angular frequency, which is omega x, which is the one that is indicated there. That depends on the direction of arrival. You see? Now, if you take all these data, by the way, you know, remember this comment. I took the story very long because you are not confident on manipulating array. You are not confident on making the processing of multidimensional signal. Okay? So since this is new for you, I took the story quite long. Okay? Just to let you smoothly enter into the topic. When you make the oral, you don't need to tell me all the story. So, you know, what I want to see is that you learn what are the approximations, right? The far field approximation, the planar wavefront approximation, and so on. Okay? You don't need to tell me all this story because I don't make an array. I don't make the oral when you just tell me all the story. Remember that. If you plan to do the oral, don't keep. You know, I don't want that you repeat all the story by memory. Okay? Don't do that. So now, what you have to do for the oral, you need to, after introducing the model, you immediately go to the signal model for the ensemble of signals. Because so far we have been considering one signal, not n. So we have n antennas. And so, you know, since we are considering n antennas, so you need to take all the n signals and model the n signals. So let's see what is the model for n signal. So the model for n signal is a vector y, which is representing the n signal, n time 1, versus time, which is the source, which is invariant versus the array. Time, you know, I have this spatial sinusoid, which is organized as a vector. But you know, if you look at this vector, that one, so this one is the spatial sinus, it's a sinusoid. So I only include the word spatial. So if I take the word spatial away, this is a sinusoid sample at the time, the first sample. This is the second sample of the sinusoid. This is the third sample of the sinusoid. So along these vectors, you can see the fluctuation of the sinusoid with a period that depends on these parameters, and mostly on omega theta. So this vector, okay, collects the information about the directional radius, plus W. W is the noise on all the sensors. So you know, in a compact form, we have ST A theta plus W. Okay. So this, you know, this model is the same model that we discussed for one sinusoidal noise. It's the same. The only difference is that in this vector, I don't put a complex sinusoid, but perhaps I put a cosine and sine. Do you remember that? We have cosine and sine. Okay. Now I only write in a compact form using a complex sinusoid because I mean it's more convenient to treat a wide general set of problems. But anyway, it's the same model that we used for cosine and sine. Because if I fragment this, you know, this vector into the real and imaginary part, then I have, you know, 1 cosine omega 0 dV sine, cosine 2 times omega 0 dV sine, blah blah blah, and then I have a second vector which is represented by the sine. So that's the same. Now, what is W? Now, WT is the noise. And by the way, is a vector of noise. So this vector of noise, in a general sense, we can consider that is Gaussian. So it is a circular Gaussian that is zero mean and with covariance RW. Now this covariance is not the covariance of time, it is a spatial covariance. This depends on space, it's the spatial property of the noise. Now the noise is temporally uncorrelated, so we say that, you know, if we take a 2 snapshot of the noise here in t and tau, then they are uncorrelated except for t equal tau. Okay. Now, in addition to that, we can assume that the source is represented by a Gaussian source, so it's Gaussian. And so the source is Gaussian with the power sigma s, sigma squared s. So that's the framework of the problem. Now, given this framework, by the way, why we are considering the source as Gaussian correlated? Because I mean, it's a very convenient way to represent a condition where I don't know what is the waveform, where the waveform for the source. So I don't know exactly how is the source. So it's a convenient way where I model, for instance, the transmission of voice or whatever. Okay, I don't know what is the voice. I represent it as a Gaussian process. Now, so assume that, you know, I don't have one directional radius, but I have a multi-directional radius, more than one. Now, I mean, up to last week, I could have said, assume that I don't have one sinusoid, I have a multiple sinusoid. Okay, so no question on that. I simply generalize. So let's generalize to the case where I have a L, capital L sinusoid. So you know it's a sum of, so it is S1 T A theta 1, okay, which is the vector representing a sinusoid, spatial sinusoid, associated to the directional variable theta 1, plus I have a source S2 time A theta 2, which is, a vector representing a spatial sinusoid associated to the direction of I theta 2, plus blah, 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 blah. Okay? So, which is condensed here. It is the sum of L terms. So, rather than representing this way, okay, I prefer to represent my problem as I collecting all the vectors representing the sinusoid in column, multiplied by one vector representing the sources. So sources number 1, sources number 2, sources number 3, blah blah, sources number L. So in conclusion, my model is yt is equal to a theta times st plus w. So that's the ensemble model. So the ensemble model is equal to a theta, theta is a vector, A is a matrix, times st, which is st is a vector of all the sources, plus wt, wt is the mass. Okay. Now, so that means I have a set of sources, many sources, L, capital L sources. Now we can further assume that the sources are Gaussian, since one was Gaussian, so the ensemble of that is Gaussian as well. And if I attempt it, so if I calculate what are the statistical properties of y, then the statistical properties of y is represented by a source st, which is represented by a Gaussian variable. Then I have a wt, which is Gaussian. And so, if I want to represent what is a y, what is the property of y? The property of y is that there is a sum of Gaussians. And so it's a sum of Gaussians at zero mean. So, y, in conclusion, y is equal to, is a Gaussian one with zero mean and covariance Rw, which is the covariance of W, and then it is A theta Rs A Hermitian. This is the covariance of y. Okay. That is the covariance of y. Now it is quite important to understand what is this function about. Now this function, this property of the y, okay, this covariance, is representing the statistical properties of different sources arranged in space. And it's important, to understand what is the rank of this matrix, which is A Hermitian Rs A. A Rs A Hermitian. This one. Now, what is the property of the rank? Now, let's move one step backward. What is the rank of a matrix? The rank of a matrix is describing the number of independent columns that are going to compose that matrix. Okay? Now, so we have y. I go back to y here. So y is obtained by linear combination. These are the coefficients of combination. It's a linear combination of columns. Each of these columns is a sinusoid. It's a spatial sinusoid. That depends on data. So, if I calculate the covariance of y, assuming that the w does not exist, the covariance of y is, the rank of the covariance of y is the rank of the number of sources. So it is, if I have a set of angular variables that are different one another, then all these columns are linear independent. Then the covariance matrix represented by A, S, and then A, Rs, and A Hermitian, it is full rank. Now, when this is rank deficient, what is rank deficient? It means that the rank is not L. Okay? When is it rank deficient? Now, let's look at two examples. Now, I have two examples that are representing two pathological situations. Now, pathological situation number one. Assume that I have a set of sources. Imagine you are in an orchestra and you are in a far field. So that means that your array is very, very far away. Okay? And you are measuring, the directional arrivals of different instruments from the orchestra. Okay, assuming of course that the orchestra is generating a narrow band signal, which is not true. Now, so what's happening in case I have these set of directional rivals, then I have two directional rivals that are one after the other. Now, if I have two directional rivals that are one after the other, it happens that I have a set of sources plus the sources SL-1 and the sources SL that have the same angle of arrival. Since they have the same angle of arrival, the matrix A contains two columns that are equal. Do you agree? Okay? Because it's like to have, since these two directional rivals they are the same, that means that the sinusoid that each of these generate is the same. So since they have the same sinusoid, that means that two columns here, they are identical. If two columns are identical, the number of linear independent columns in matrix A is not L, but it is L minus 1. So that is one situation, the most trivial one that you can you isolate as a rank deficient situation. So if you try to distinguish between SL minus 1 and SL, you can't. You cannot distinguish them because they are indistinguishable in directional rivals. They might be distinguishable in another way, but they are indistinguishable in directional rivals. So this is the case, is rank deficient in case of a directional rival alignment. Now let's consider another case which is less obvious. Okay. Assume, and this happens quite often in wave field propagation. Like assume that I have a source number 1, number 2, blah blah blah. Then I have a source number L minus 1. But the signal from the source L minus 1 is bouncing on the wall and is impinging to the array from another directional arrival. So it's the same source, but it's just impinging from another direction. Now, so it's coming from another way. Now, you might be tempted to say that this situation has a rank that is L. But, let's look at carefully and why it is not L. I need a little bit of space. I will repeat it. I will make it again. Why is not L? Because if I look at the matrix on the top, okay, I have YE, okay, which is equal to, then I have a my matrix, okay, my matrix, I take the matrix and I partition in two blocks. So I have A1, A2, blah blah, A, L minus 2, and then I have A, L minus 1, A, N, okay. Then I have the sources. So I have S1, blah blah blah, Sn minus 2, then I have Sn minus 1 and Sn. Now, let me sum this to that. So let me make the multiplication of that. So I just isolated this part, called A prime, and then I put this one into S prime. And then I have the other. So Yk is equal to A prime. Now A prime is all the directional rivals are, independent, and then it's full rank. So that one is, no, it's not L, it's N. L. Okay, so A prime has a full rank, and the rank is equal to L minus 2. So I have S prime times A prime times S prime plus, then I have A theta L minus 1 times S L minus 1 plus A theta L times SL. But now SL minus 1 and SL, they're coming from the same source. So I can group because SL minus 1 and SL are the same. So collecting these two, these are A theta M minus 1 plus A theta L, that are two directional radial different, times SL. So, you know, these two vectors, okay, they can be grouped in one equivalent vector. So I have L minus 2 vectors that are linearly dependent, plus one vector that is compound of the two that is linearly dependent. So the rank now is, the total rank is L minus 1. So again, it's rank deficient. So you have two situations where the system or the signal that you get and the corresponding covariance that you get is linearly, is rank deficient. And one condition is when you have two directional rivals that are perfectly aligned. And the second case is when you have the two sources that are perfectly correlated. Now the second case happens because, for instance, if you're talking in telecommunication, you have the signal that is bouncing on the wall. And so that means that it appears as if it is a new signal, but it's coming from the same source. So it's not enriching the rank of the system. It's not augmenting the rank of the system. Now, let me, before design, let me look at that. You know, assume now that I want to estimate the take it away. Okay, so this one is the covariance of the signal that you measure. So this is what you receive. Remember, in your problem, most of the time, you don't know S. So ST in general is not known. Okay? Because it might be the signal generated by these different instruments. It might be the signal generated by different cellular phones. And so you don't know what is the signal generated by each individual source. So that means ST is not known, but model as a stochastic source. Okay. Number one. Number two, theta, which are the directional rivals, okay, are not known, but constant in time. That means that if you take a different snapshot, many snapshots, you know, they are still there. Okay. So, looking at this problem, the goal is to say, can I estimate theta from this model, okay, just knowing the mechanism, the generation mechanism, which is, you know, generated by a set of symbols. Now the question is easy. The question is, yes, we already said it. We can make the maximum likelihood estimation. Okay, we can make the maximum likelihood. So, you know, when we make the maximum likelihood, what I need to do, I need to write the likelihood function. But that is a Gaussian. So I can write the Gaussian likelihood, the likelihood for Gaussian. Then I can optimize, now with respect to what? With respect to the covariance. if you remember, when we wrote the likelihood method and we derived the maximum likelihood, well, in all cases, or in most of the cases, we assumed that the covariance of the noise was known, and we only had to estimate the mean, or something that is related to the mean. And then what I did, at that time, I said, the problem when we need to estimate something that is embedded into the covariance is a problem that we deal later. Now is the time to go back and look at that one. I just highlighted that, and if you go, you see that to be discussed later. Later is not. Okay? So these are from the chapter 7. This is handwritten, so this is this one, this chapter. For those of you that this is this chapter, okay? In this chapter I said, what about if I have a model where I have a set of observations like here, okay? I have a set of observations in Excel, which are modeled as Gaussian with a covariance C theta. Now the only difference is that this one is complex, but the problem is the same. Now, if this is the case, then we can say that each observation is modeled as a zero mean Gaussian random variable with covariance C theta. Let me go there. Every observation is modeled as a complex Gaussian with zero mean and a certain covariance. Now, let me call this covariance C theta. Okay? So I flip back. So that means that my goal here, that depends on certain parameters like autoregressive, spectral analysis, frequency, DOA estimation with the random alpha, which is a random coefficient. Okay? So that is the problem. Now, with multiple independent observation, okay, so x1, x2, blah blah, xl. Okay, now L is confusing, so it's many observations. So what I can do is I can find the log likelihood, which is calculated this way, where Rx is the sample estimate of the correlation matrix. So that means that I can calculate this part, and I need to optimize with respect to that. That means that I can calculate the log likelihood function, and I can calculate the maximum likelihood method. Now it's more complex. Okay. The only I do is that I'm not solving, just to say the method is more complex. So, we are touching, let me say, the end of the course. So we are touching the end of the semester. So let me say, from my point of view, you are ready to understand that these concepts that are a little bit more evolved than when we started in September, when you were younger, you were less malicious, less open to this kind of evolution. Okay. So anyway, there is a way to do it. If it is for the special case that is not structured. What does it mean not structured? Not structured means that the covariance has no structure. If the covariance has no structure, means that there is no structure in the covariance. But this one is a structure, because the structure is due to the fact that this is noise. If it is wide, it's even simplified, but this covariance has a structure. So that means that we cannot take these examples. Okay, this is a special case. So our method stops here, and it's complex. So since the directional reference is important in life, and the people have developed several methods to estimate the directional arrivals in case of configurations that are complicated. And so there are some methods to optimize this function. Rather than optimizing that, you optimize something similar, okay? Or you use some algebraic properties. And so you get some high resolution method for directional arrival estimation. We are not touching that. Once again, what I'm talking now is putting the bound to what we don't do, okay? But just to tell you that there is much more than what we are discussing. So now going to to be discussed later. Let me put it here. So we revised on. So we have been waiting till 14 December. Okay, and probably this note I wrote probably 1.5 months ago. Okay, so just to tell you that the concepts are linked together. There is no way. So like computing the integral, you cannot forget to compute the integral. It's like the derivative, you cannot forget to compute the derivative. Okay, so at least for your professional life. No, so far I said nothing about what is the spacing. Okay, so the spacing is same spacing for sampling the sinusoid, and the sinusoid is sinusoid in space. So what is the frequency of these sinusoid? The frequency of this sinusoid is fx. Okay? So what is the sampling theorem? The sampling theorem says that the frequency. I know I'm out of time. Give me 1 second just to make the final derivation. So I have fx, okay, and just almost copying that. So which is f0 divided by v then time sine theta. Okay. So this is the frequency. Now this sinusoid is a frequency in space, which is measured by cycle per meter. Okay. So now this is a frequency. So you remember what I canceled? I said, okay, if I have a sinusoid, okay, this sinusoid has a certain frequency. My sampling frequency should be at least 2 times that frequency. So what is my sampling frequency? 1/d is the spatial sampling frequency. Okay? So the sampling frequency should be larger or equal than what? 2 times f max. That's the sampling theorem applied to the array of sensor. Okay, so f max is in this case is the maximum frequency here, which is 2 times fx, because I have 1 frequency only. Then this 2 times fx is 2 times f0 divided by v sine theta. And so then I can calculate what is the spacing. And so the spacing d should be smaller or equal than v divided by 2 times f0. And then it is 1 sine theta. But this guy here is lambda. So this one is lambda divided by 2, which is half of the period. But this period is the period that is a sample. So it is sine theta. Okay? Or it is lambda x divided by 2, which is half of the period. So if I need to sample, the sampling interval should be smaller than half of the period. If you go 2 pages before, which is when we started, this is exactly the same relationship. So then this justifies the assumption. And the worst case for that is when sine theta, okay, this has to be smaller than this. Okay, so the smallest one is when this sine of theta is equal to 1. So then d is smaller than lambda divided by 2. So that is the extreme case. D smaller or equal lambda divided by 2 is the extreme case. So lambda, so the spacing, the sensor spacing, is less or equal half of the wavelength. This is the extreme case. So in this case, the sensor spacing is always valid. Is always valid. Now we continue on that next week, discussing some special cases. Okay, Because remember, this, you know, the spacing or the frequency depends on direction arrival. So for instance, if I rotate my array, then I can change my frequency. Okay? And so, you know, next week I will explain why there are, if you go to the airport, the antenna keeps rotating. There is an array, usually, you know, it's 2 meters, 2.5 meters, okay, which keeps rotating all the time. And it keeps rotating because it has to cope with aliasing conditions. We'll talk about that next week. Okay? Enjoy the weekend.